right. Happy Wednesday morning, everyone. Good job on finding the correct room. You'll notice this room is a little more spacious, but the key feature for me is that I plug in my technology and it works, and I don't have to switch cables or adapters or anything. We also have kind of a better blackboard should the technology fail. So thank you for being willing to move next door. I'm going to jump right into it. Last night, about 10:30-ish, I posted an announcement on Brightspace, and I will, so if you haven't checked your email, you'll have received an email announcement about that. So please go look at that today. It has, among the announcements, was the room change, but there are a couple other things that will help you progress. So our agenda for today is we're going to do a quick review of scientific notation and unit conversion. And then we're going to finish chapter 1 by doing a little brief discussion of density as a characteristic property that can distinguish different materials from one another. And that will be our team exercise for the day. And then we're going to begin talking about the history of atomic theory and the structure of the atom. Okay. So, if you recall, last time we ended with essentially a unit conversion problem, but we had to go through two different units to get the information we needed. So, I was talking with one of your peers, and there is an abundance well, not an abundance, but there's some math review in your homework that uses concepts that we won't necessarily be applying this chapter or maybe even all semester, but within a 2-semester Gen Chem course you use. But what I will try to do is when we do have problem solving and math things, I'll try to kind of emphasize and articulate what the mathematical principle that we will be using is. So for the first 2 chapters of your textbook, okay, essentially we are using 2 mathematical principles, scientific notation and unit conversion. Okay, so for scientific notation, and I'm going to, I'll skip to my blank sheet here. Okay, so scientific notation, we're going to be expressing numbers using what we call exponential notation, or times 10 to the something, so the powers of 10 notation. So we can use it for very small numbers, okay? Or we can use it for big numbers. All right? And so when we use scientific notation, what we're going to do is we're going to take the number part of the number that's either all the way on the right if it is a small number, or all the way on the left if it is a big number. Okay, so we've got our small number, and we're looking here, and we're going to express that with, as a decimal number. So I'm going to put my decimal in between the 4 and 8. So it's going to be 4.82, and it's going to be times 10 to the something. If it is a tiny number, okay, as it is up here, that it is going to be a negative exponent. Okay. If it is a large number, it's going to be a positive one. So here's the number that I would write, 5.73 times 10 to the, and it's going to be a positive number. How we figure out what that number is just counting how many positions we need to move that number over, okay? So, or that decimal point over. So in this case, we'd have to move it 1, 2, 3, 4. Okay, so it would be 10 to the minus 4 is going to be the exponent for that, writing that in scientific notation. When we're dealing with big numbers, we're moving over to the right. Okay, so one thing I should have said, written, is the decimal point for that number is right there when it's written out as a full number, right? So let's move our decimal 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So that's 5.73 times 10 to the 11th. Okay. So the other thing that we talked about was using metric prefixes. Okay. And so we can use metric prefixes to replace the times 10 to the something. So let's just say that for this number it's grams, and this unit is liters, okay? Oops. All right, and so instead of saying 5.73 times 10 to the 11th liters, I want to use a prefix to replace the times 10 to the 11th, okay? Well, if we go back to our prefixes, if I can find our, oops. Here are our prefixes, right? So we don't really have one that's times 10 to the 11th, right? We have one that's times 10 to the 6th. Oh, I didn't give you a chart that went up to 9. So let's change. Sorry about that. Well, no, let's say 10 to the 6th is the biggest that we have, okay? So let's say we want to express that times 10 to the 11th number in units of megaliters. Okay, so mega is times 10 to the 6th. So let's go back here. We're working with what we have. Okay, so 10 to the 6th equals a capital M mega. Okay, so we're going to use this as megaliters. Okay, and 10 to the 6th is 5 orders of magnitude smaller than 10 to the 11th, right? So if I go back to my number here, okay, and I say I'm only going to move it over 6 decimal places, that's going to tell me what number to write there, okay? So I would go 1, 2, 3, 4, 5, 6, okay? So I would have 1, 2, 3, 4 zeros, 1, 2, 3, 4 zeros, and then my 573. And so that's how I could, write that number using a metric prefix. Okay? Now, it's going to be a little, so we're going to replace 10 to the whatever with an appropriate prefix. And we might need to adjust the number that's in front, again, depending on how far we are off. Okay, so let's look at 10 to the minus 4. This one's going to be a little bit easier. So if we go back to our table, okay, we've got a prefix that is close, right? We have 10 to the minus 3, okay? And that's milli. All right, so if we go back here, okay, and we want to express this in milligrams, which is times 10 to the minus 3 grams, okay? So here we have times 10 to the minus 4, okay? So again, to figure out what the number in front of the milli should be, we go back to our number here, 4.82, and remember that the number we chose for the exponent was, how many places we move the decimal over, okay? So if we're moving it over only 3 instead of 4, we'll go 1, 2, 3. Whoops, hang on. It went the wrong way. Sorry. 1, 2, 3, okay? That would put the decimal point, so if it was 10 to the minus 3, that would put the decimal point right before the number 4, okay? So this number in milligrams, is 0.482 milligrams. Yeah?
So like if the scientific notation isn't there and I use the prefix, like if you write mg or ml, how do you know if it's milli or mega, you know?
So, all right. So because each of the units has its own associated symbol with it, okay? So mega is capital M, kilo is little k, milli is little m, micro is the Greek letter mu, okay? So what is, the more likely situation, right, is that you'll see a number, say, oh, this aspirin tablet has 200 milligrams of acetylsalicylic acid in it. And if you wanted to know what that was in grams, okay, because you're trying to measure it on a scale, you would take the milli, right? So if we take, 200 milligrams, and we want to know how many grams it is, right? We would replace the milli with times 10 to the minus 3, because that's what that means. 200 times 10 to the minus 3 grams, okay? We want to write it just as a number all the way out, okay? So it's a negative exponent, so that means it's a small number, so that means we're going to be moving the decimal point this way, okay? So if we do that, if we've got 200 and we're moving 1, 2, 3, it's going to be 0.2 grams, okay? So, this is kind of the more common, when chemists are working in the lab, there are certain units we're really used to going back and forth between. So I'm mainly a biochemist by trade, and we use really tiny volumes and really low concentrations. So we're going back and forth between milliliters and microliters all the time. And those are sort of by a factor of 3. So you eventually get it in your head that 0.5 milliliters is 500 microliters, and it helps you in picking the measurement device that you're going to be working with. But for now, since we're just starting out, it's a little more kind of we have to think it through all the way. Okay. But it does help us, be very efficient with our with expressing our numbers. So scientific notation, that's our, again, mathematical concept number 1. Mathematical concept number 2, okay, is the fact that when you have a fraction that has 2 things that are the same on the top and bottom, you can cancel them out, okay? So, and that is the mathematical principle behind this procedure called dimensional analysis that we've been using to, do unit conversions, okay? So canceling units, okay? So when a fraction has the same exact thing on the top and bottom, that thing can be canceled. So if we go up here and we look at our team question from last class, okay? And we were doing this process of converting one unit to another, okay? What I've shown up here is I show myself crossing out the units, okay? But let's say I didn't cross out the units and I just multiplied this thing by this thing by this thing, right? If I multiply these things, okay, what units would my final number have? Okay, well, if I did that, okay, and I'm going to write it over on the left here, the top would be pounds, kilogram, stone. So pounds, kilogram, stone, divided by pounds, kilogram, divided by pounds, kilogram, okay? And so, my basic algebra tells me that if it's the same on the top and the bottom, I can cancel it out. So my pounds can cancel, my kilograms can cancel. So it doesn't matter if you do it along the way, like my habit is when I'm doing dimensional analysis, like this right here, or if you just carry your units all the way through, see what you have at the end and say, oh yeah, these things are the same, those things are the same. Okay, so we're also going to see when we get to later on in the course, when we're we're doing something called net ionic equations. So we're trying to figure out, all this stuff, we've got all these particles in our solution, and only a few of them are actually engaging in a chemical reaction, and we want to write an equation, an expression that describes only the stuff that changes, okay? We're going to write these equations that have a whole bunch of stuff on the left and a whole bunch of stuff on the right. And we're going to use the same principle that if I have something that's exactly the same on both sides, I can cancel it out because, it hasn't changed anything, okay? So those are our two, foundational mathematical principles that we're just going to be applying, kind of over and over again. So the last unit conversion thing I want to do, because I personally find this conceptually difficult as well, is what happens if you have this nice, conversion factor table, and the numbers that you're dealing with have different dimensions on the units that are in your conversion table, okay? So here we are. And I have a volume of 3.51 meters cubed, and I want to convert it to cubic feet. Okay? Well, I know I have a unit conversion between meters and feet, okay? But I don't know, how that translates into, when I've cubed that thing, right? So, excuse me. So what we can do is we can make our own composite unit conversion factor by taking our original one. So we've got 1 meter equals 3.28 feet. Okay. In math, if I do something to one side of an equation and the other side of equation, and I do the same thing, it's okay, right? If I multiply both sides by 5, it's fine, right? I haven't really changed the relationship, okay? So what I'm going to do is I'm going to cube both sides of this, okay? So I'm going to say, okay, if I multiply this by itself 3 times, okay, what do I get? Okay, so this is the number 1, so it's going to wind up being 1 meter cubed. And so, got 3.28 times 3.28 times 3.28. And so that equals 35.29 feet cubed. Okay? So now this is going to be the same exact process as any other unit conversion. Okay? I'm going to take my number, 3.51 meters cubed. Is everybody okay with, I wrote the thing out here, but is everybody good with that? M to the 3 is the same as meters cubed? Okay. All right. And so I want to multiply it by a conversion factor, and I want to wind up with cubic feet. So I've got my conversion factor here. Okay, so what is going to be on the bottom? What unit is going to be on the bottom first? Is it going to be my meters cubed or my feet cubed? It's going to be the meters cubed. Okay. And the feet cubed is going to be up here. What number is going to be on the bottom? Is it going to be 1 or is it going to be 35.29? It's going to be 1, right? Because when I have a unit conversion, the number always stays with the unit, okay? So the top is going to be 35.29. So 35.29 times 3.51 gives us 123.86, okay? And again, our units that are the same on the top and the bottom cancel, and it leaves us with what we want, okay? All right, so we've achieved our first goal for the day. So let's give ourselves a little cheer and just cross it off, all right? Okay, so our next goal for the day is to talk about density, okay? Does anybody have any lingering questions about scientific notation, unit conversion, or metric prefixes? Okay, so what I'm going to do is I'm going to pass around this little tray, and we should have time for everybody to at least see it by the end of class. And what it has is it has 1 centimeter cubes, and they're of different materials. So this one has Br on it, that's brass. We have carbon, we have zinc, copper, aluminum, what else do we have? Iron, and tungsten. All right, and so, just pick each of them up, and what I want you to do with these is they're all the same exact size, but you'll notice that they feel different, okay? And that's because they are different densities. So one of the properties that is a characteristic property of matter, okay, is that the particles, whether they're atoms or molecules, okay, that make up that material, okay, they take up a certain amount of space, okay? And the amount of space that they take up on a per particle basis differs based on the material, okay? And so if you have a lot of mass, okay, concentrated in a small space, okay, we would call that material more dense, okay? Materials that are less dense, okay, are going to be materials that have less matter per unit of space. Okay, so as you're feeling those cubes, they all are the same amount of space. Okay, and the ones that feel heavier, okay, they're heavier because they've got more matter packed into that little amount of space. So when we talk about density, okay, it's the amount of mass of a material divided by the amount of volume or the amount of space it takes up. Okay? And the standard unit that we use for this is grams per milliliter. Okay? So grams is a unit of mass, right? And milliliter is a unit of volume. In medical applications, the unit of milliliters is often replaced with cc's, which stands for cubic centimeters. A cubic centimeter is the same thing as a milliliter. So occasionally you'll see densities listed as grams per cubic centimeter. Okay, so just to let you know, 1 milliliter equals 1 centimeter cubed. And again, in medical situations, especially with injectables, you'll see the abbreviation cc used, and that just means cubic centimeter. Okay. All right, so excuse me. So here's just a list of, materials and their densities. Okay, water has a density of 1 gram per milliliter, but you'll notice that ice, okay, has a lower density, right? So the solid form of water has a lower density than the liquid form, and this is because water does something called hydrogen bonding with itself. So water molecules have an interaction with themselves that when you cool the material down and the molecules move slower, they wind up forming these networks of interactions that hold the molecules farther apart. Okay? And so the material is less dense, and materials that are less dense will float on materials that are more dense. Okay? So there is a famous picture that was taken in the 1970s that I have lost, but I used to show when I taught my gen ed chem class years ago. And it was a mercury mine worker in the old Soviet Union, and he is laying on a pool of liquid mercury. Mercury is an element that's very toxic, liquid at room temperature, and is extremely, extremely dense. And so, so a human could stand on it, sit on it, lay on it, and they would float. They wouldn't sink, even though it was a liquid. Okay. All right. So you can tell materials apart based on their density. Now, it's not going to be enough information to reliably narrow down and identify a material, chemically, but it's a good first shot at telling whether in, say, a forensic application, if somebody is claiming something is 100% gold versus, 50% gold, right? You could easily just weigh the thing, put it in water to see what its volume was by displacement, calculate its density, and pure gold is going to have a much different density than gold mixed with another metal. Okay, so you can't say, oh, this statue that you're saying is gold is actually brass, but you can say, well, it's not 100% gold, and we need to analyze it further to determine exactly what it is. So density is actually a really useful property of material, and it's used in lots of applications, not just forensics. All right, so to give you a little practice with both your unit conversion and calculating your density. Who remembers what my favorite element was from the first day of class? Copper. All right. So this was a really fun infographic that I found. Okay, that it has to scale pictures of what $1,000 of different materials would look like. Okay, so you can see that the things that we consider more precious, like silver, are these tiny little bits, and lead and aluminum are much cheaper. Okay, so in this infographic, you have two pieces of information. Okay, you are given the size of the cube, okay, and you're given the material it's made of. Okay, so your goals, okay, for your team question for today, okay, are going to be figuring out how much $1,000 of copper would weigh. So you should be able to determine the volume of that cube, right? And what's the piece of information you have to look up? So what's the chemical concept we're talking about right now? Density. So if you know the density and you know the volume, you can figure out what the mass would be. Okay? All right. So lucky for you, I've done that for you. Okay, so I'm going to pass around these blue sheets. Turn around, talk to your neighbors, figure out how much that amount, $1,000 of copper would weigh in kilograms, or in grams, sorry. And then figure out how much it would be in pounds. So you're going to have to convert grams to kilograms before you go to pounds. Okay? All right. So I'm going to make you the epicenter of, and maybe you guys, well, you guys can do this, right? You guys you can talk. All right. Everybody got a little group they can work with? All right. All right, so I'll give you 3-4 minutes, and then we'll work it out. So it's 24, 24.6. Oh, that's just that amount of power. So a cube that's that size. Okay, so figure out the volume from the edge. Okay, so that's easier. All right, so the room has quieted a little bit. So I'm going to do the first step up here, right? So density is mass divided by volume. So we know the density, okay? And the volume we can get from the edge of that cube, okay? So our volume is going to be what? 24.6 centimeters. And we have a cube, so it's 24.6 times 24.6 times 24.6, right? Oops. And that comes out to be a nice large number, 14,886.93 centimeters cubed. All right. So next we have to apply this to figuring out what the mass is, correct? All right. And again, going back to our mathematical principles, if I do one thing to one side of an equation and I do the same thing to the other side of the equation, it's okay, right? So if I want to move the volume so that I'm just solving this equation for mass, we can multiply both sides by volume. So I can multiply by volume here, and I can multiply by volume here, and that's how I get rid of the volume on the right-hand side. And now I have an expression that's mass equals volume times density. Okay, so my mass is going to be equal to my volume, which is 14,886.93 centimeters cubed, times my density, which is 8.96 grams per centimeters cubed. Do I have any units that are going to cancel out for me? Yes. Baseball cap with New York on the top. What's going to cancel? Centimeters. That's centimeters cubed. Great. All right. Any of the groups get to calculating this number? What'd you get? 133,387. Yep. 133,387, right? All right, and that's going to be grams. Who here thinks in grams? Oh, good. 2 people think in grams. The rest of us probably think, growing up in the U.S., we think in like pounds or ounces, right? So let's convert this to pounds, all right? So we have a, kilogram to 2.2 pounds, all right? So we're going to start out by converting to kilograms. Now, I've been doing this for more years than I want to admit to you, so I can do that in my head, but we're going to be explicit about it and do dimensional analysis. So we've got 133,387 grams. Okay. 1 kilogram. How many grams is 1 kilogram? It's 1,000, right? So it's 1,000 grams. Also known as, what would that number be in scientific notation? it would be 10 to the 3, because it's bigger than 0, right? Yeah. So we're going to multiply that by a kilogram divided by 1,000 grams, so that our grams will cancel, okay? And now we want to convert our grams into pounds, okay? So we're going to use this conversion factor up here. We want to wind up with pounds, so the pounds and its number stay up top, and LBS is the abbreviation for pounds, and 1 kilogram there. And that number in the end winds up being 293 pounds, okay? So you can get 293 pounds of copper for $1,000, or at least as of the time that this infographic was made, okay? Yeah?
So that's equal to 1,333 kilograms?
It's equal to 133 kilograms. So if you just do this part right here, and you divide this by 1,000, that's 133 kilograms. Yep. So if you multiply 133 kilograms by 2.2, because there's 2 pounds roughly per kilogram, that's how you get your 293. Okay? All right. Give yourself a round of applause. You finished chapter 1. Yay! All right. So we're going to start